Nvidia just committed $4 billion to two companies most people have never heard of. Not chip companies, not GPU manufacturers, photonics companies. Companies that build infrastructure out of light. Jensen Huang called it building the next generation of gigawatt-scale AI factories. Factories built on light. If you understand what that means, you already know why this changes everything. If not, that is exactly what this video is about. I went into this story thinking it was about chips. That is where every headline points. Transistors shrinking, the 3-nanometer wall. But the deeper I got into the engineering research, one word kept appearing: not chip, not transistor, interconnect. The connection between chips is the actual bottleneck in the next generation of AI clusters. And when I understood why, it changed how I think about infrastructure entirely. Here is what happens inside a modern AI training cluster. Tens of thousands of GPUs working in parallel, each one doing extraordinary computation on its own. But training a frontier model means those GPUs are in constant conversation, passing gradient updates, synchronizing parameters, moving activations across the network billions of times per second. Engineers call this collective communication. It is the invisible architecture underneath every large language model you have ever used. What carries those signals? Between GPUs, copper. Electrical signals moving through metal, and copper at the speed and density that next generation AI clusters require runs into physics it cannot negotiate with. 3 problems. First, resistance. Every signal through copper converts energy into heat. At the scale of 100,000 GPU cluster, that heat becomes the dominant engineering variable. Second, signal loss. Electrical signals degrade over distance, faster or farther, but not both. Third, energy per bit. Moving a single bit electrically has an energy cost, small but real. When you move petabytes per second inside a training cluster, the energy cost of wires alone shows up on the operating budget. I manage 62 Azure subscriptions. I deploy infrastructure under air raid sirens. I understand physical constraints. And this one is real. Copper is not failing. It's hitting a ceiling that no engineering decision can remove. Friction is a property of the medium itself. Photons work differently. Light carries no charge. It generates no resistive heat. It does not degrade over distance. And through wavelength division multiplexing, you can send dozens of independent data streams through a single optical channel simultaneously, each riding a different color of light with zero interference. That is why a single fiber optic cable carries the internet traffic of an entire continent. This physics has existed for decades in telecommunications. What is happening now is engineers building that same physics down to the scale of a chip, down to the connection between two GPUs sitting centimeters apart. MIT research shows photonic hardware performing matrix multiplications, the core operation in every neural network, at the speed of light. Energy reduction over 90% for certain operations compared to electronic equivalents. 90% is not an incremental improvement. That is a different physical substrate doing the same work. Light Matter, founded out of MIT, built a photonic inference accelerator called Passage, raised over $400 million. Went from university lab to production in under 7 years. Nvidia put $2 billion into Lumenium and $2 billion into Coherent. $4 billion total. This is a company that previously chose copper over photonics, where copper made sense. The $4 billion tells you exactly where copper stops making sense. Every major hardware transition in computing created a new class of engineers who understood the new substrate before most people knew it existed. Multi-core, GPUs, cloud. Each time, early understanding was a career multiplier. Photonics is the next substrate shift. The role that becomes valuable is what I call the AI systems architect. Someone who understands how light moves through silicon waveguides, how that affects bandwidth and latency at the cluster level, how those physical properties cascade into distributed training and inference. We did not hit a wall, we found a better medium to think in. The models you will use in 2028 may owe a significant part of their capability to the fact that the wires finally got out of the way. DevOpsDive.com